Okay, I want to look at some more homework problems from Chapter 5 and Chapter 6. Okay, so this is tile number 3. So I have this entire PDF posted on our module for this week. And what I'm going to do is as I go through this, anything new I put on here, I'm going to put in that color so that it will distinguish itself from what I previously did. Okay, so number 3. Okay, so the confusing thing is they give you two horizontal forces. Okay, now what that means is imagine you have your calculator on the table, and there's two forces that act on the calculator, and those forces are parallel to the table. So imagine the table is the XY axis. So what I did is I just drew a top view. Okay, here's a disk, and they tell me that F1 is to the right. Okay, there's F1. And they tell you there's another force, F2, but they don't tell you, let's see. They don't tell you exactly where F2 is, so I drew it there, and I drew it there. Okay, because they want to ask what's the, they're asking what's the angle between those two forces. I don't know if F2 is up here, or I don't know if F2 is down over there. Okay, so to find that, what I did is I drew, okay, so there's my coordinate system. I want to find the angle. All right, so from the graph, this is velocity in the x direction versus time. So you know from what I think our first lab, the lab with the dots, that if you have a graph of velocity versus time, the slope of that graph is the acceleration. Okay, so the acceleration in the x direction is just the slope of that line. So rise over run. So I can go to that line, and when I did my slope, I used that point, and I did my change in vertical over change in horizontal, and that gave me the slope of the line. So that gives me the acceleration in the x direction. Okay, so then, okay, so I'm trying to find that angle. So I redrew the picture here. Okay, so if I do F equals ma in the x direction, looking at my picture, well, F1 points to the right, F2, regardless of what quadrant it's in, the x component is still F2 cosine. So net force is equal to max. So you have everything in here. You have F1 as a number, you have F2 as a number, you have the mass. Where's the mass? They give the mass. So you have the mass as a number, and the acceleration is just the slope of that line above that, and then you can solve for the angle. Okay. All right, so number 5, so what I did, okay, if you're not sure what this exactly looks like, just take that part, okay, Google that, and there's a picture of this person pulling the train with their teeth. Okay, so they're not moving uphill, okay, it's the rope or the cable that's tilted up. So I just drew a side view over here. So what I did, this is the train, okay, train of mass capital M. His mass is mass little m. So I drew the forces that acted on the train. So you got the tension, okay, you got the weight of the train, you got the normal force, okay, and they're saying there's no resistive friction force. Okay, so I'm going to do the 5-step method, but let's see, what do they ask you to find? They want you to find the speed. Okay, so if you do F equal ma, there's no v in that. So what we have to do is they give you initial velocity, they give you a distance, and they want a final velocity. That reminds you of equation number 3. So I wrote equation 3, that's 0. Solve for v final. So I know delta x, so now it comes down to finding a. Okay, so now it's a Newton's second law problem. So go back to the picture. I have my picture, I have my forces, coordinate system. Okay, I broke up tension. There's my t cosine. Okay, there's my t sine. Put two little lines through it. Okay, and then I just step 5 is just apply F equal ma in the x direction. Now again, I'm applying this to the train. That's the mass of the train. Okay, so be careful. You have two different m's. You get the capital M, mass of the train, little m, the mass of the person. Okay, so look at my picture. The only force I have in the x direction is t cosine. That's equal to ma. Okay, so I'm trying to find a. Okay, so I solve this for a. Okay, all right, so I'm going to take this a. Okay, I'll call this, let's see, I'll call this equation 1. That's equation 2. So I'm going to take equation 2 and I'm going to put it into equation 1 right there for A. So V final is 2A delta x. So this whole thing here is A. Okay, my T cosine over capital M. Okay, now if you look back here, they don't give you the mass of the train, they give you the weight of the train. Okay, so obviously you could off to the side calculate the weight, right? Because weight is mass times gravity. Okay, but what I did is I just multiplied top and bottom by G. Okay, multiplied by 1. So on the bottom, that's the weight of the train. They give me that. So all I have to do, okay, is I get to use the weight of the train, but then I have this extra G that floats around right there. Okay, so I put in everything, and that gives me the final speed after they've gone that far. Oops, and I forgot the tension here. They tell me that the tension in the string is 2.7 times his weight. So the tension in the string is 2.7 times his weight, and his mass is little m. So that's why I put in tension is 2.7 little mg. Okay, so this problem here takes a little while to figure out what they mean. Okay, but everything is happening horizontally. Okay, so the person's standing over here. Here's the fishing line. Fish is headed to the right. Okay, so it's going horizontally. So velocity is to the right, but it's slowing down. Okay, so the tension in the fishing line is slowing the fish down. So that's why the acceleration points to the left. Okay, so the acceleration is negative. That's why I picked my coordinate system. Okay, like that. All right, and I'm trying to find, okay, I want to find what's the minimum tension required to stop that fish, okay, if it's initially going at that speed. So initial speed is my 2.8, final speed is 0, okay, and they give me a distance. So I have initial velocity, final velocity, and a distance. That reminds me of equation number 3. So I wrote equation 3. Okay, and that means I can solve for A. Okay, because I know V initial, I know that. So A is now a number. That's done. Okay, so if I had started with Newton's second law to find the tension, I'm trying to find the tension. Okay, I have a picture. Here's the forces on the fish. I don't need the weight or the normal force. Okay, everything's happening in the x direction. Okay, so there'd also, well, the normal force would be a buoyant force, but don't worry about that. Okay, so my picture, I'm applying F equal ma in the x direction to the fish. The only force I have is tension. That points backwards. That's why I have the minus sign. That's equal to ma. Okay, so I wrote down minus t is equal to m, and then my a, I put in that. Okay, and then I don't have the mass of the fish. They give you the weight. Okay, so again, you can obviously, if you want, you could find the mass of the fish, just solve that for m. I just multiply top and bottom here by g. So here, mg, that's the weight of the fish. Okay, and then doing that, you still have to put in little g there. Okay, and that gives you the minimum tension to stop it, stop that weight of a fish that was moving initially that speed in 12 centimeters. Okay, so this is also from chapter 5. Okay, so I have an electron moving to, let's say it moves to the right. Okay, and actually you'll do this maybe in the first third of physics 196. When you have an electron and it moves maybe in a magnetic field, it gets deflected, there's a force on it. So I'm trying to show that this is analogous to projectile motion. Okay, here's your projectile, shot it to the right. There's always a constant force, okay, constant force of mg downward. And if the force is constant, then the acceleration is constant. That's what's happening here. They tell you you have a constant vertical force. So there's this constant vertical force, which means you have a constant upward acceleration. So if you take this whole picture and you flip it over, it looks like the projectile. Okay, so I'm treating it like a projectile. Well, essentially that's what it is. Okay, so I have, well, it's acting like a projectile. There's a constant upward force. So there's my electron. V initial is the same V initial x because it's going horizontally. And I want to find how far it's deflected vertically. Okay, so they give me, let's see, I want to find that vertical distance. Okay, so if I do F equal ma, there's no vertical distance delta y in F equal ma, so that's why I'm doing projectile motion. So let's see. I don't know V final. Okay, so that's why I'm using equation number 2. So V initial y is 0. Okay, and then let's see. Then I could solve this for ay. Okay, so let's see what we can do here. So I'm trying to find that distance. Okay, so I'm trying to find delta y. Okay, all I need here is I need to find the acceleration. Now it becomes a Newton's second law 5-step method. So there's my picture. Okay, I have that constant force on it. I could draw that, some upward force. Okay, and so I want to find the acceleration. I need that for right there. So I'm doing F equal ma in the y direction. All right, so all I have is that force that points up, and the acceleration is upward. So if I solve for A, I have net force over m. So they give me the force, and they give me the mass. So I have A. So right here, I have delta y is 1/2 ayt squared. So I put in what A is. That's A. It's a net force over m. Okay, and I need to find t. That's the same thing you did in this lab here. You had to find the time it takes to hit the ground, time it takes to fall that distance. Well, you go back to the lab. All right. Let's see. They tell you delta x. They tell you how far over it's gone. Okay. So then I can use equation number 2 in the x direction, solve this for t. Okay. And then I take this t and put it right there. And so I have 1/2 at squared. And then just be careful of the units. Okay. And then I showed that the units do indeed give you meters. Okay. So this picture is perfectly analogous to the projectile problem you did. You had the projectile under the influence of a constant gravitational force. Here's the electron under the influence of some other constant force that it falls to the ground. Okay. Well, actually, I drew it going up. I could have drawn it going down. Either way, it's deflected. That delta y is deflected up or down by 13. Whoops, it's deflected up or down by that 0.144 millimeters. Okay, so question 12. Okay, this is still chapter 5. Yep, still chapter 5. Okay, so you're trying to lower. Okay, so you have a rope that'll snap if the tension exceeds 393. So you have a box of stuff that weighs 437. Okay, so if you had to hold that whole box constant, okay, the weight of the box is 437. Okay, if it's not moving, you would have to have a tension of 437. Okay, so that rope will break at 393. So you can't hold that steady. So for that, with that rope, you would have to lower it rapidly. You'd have to accelerate it downward. So I wrote that for the rope not to break, you have to accelerate the box downward to lessen the tension. And that's the exact same thing as if you get an elevator, okay, and if elevator is at the top floor and it starts to speed up going down, okay, you feel lighter in the elevator when the speed is increasing downward. It's the exact same thing as what's happening to the rope. Okay, so for part A, I want the acceleration that'll put the rope on the verge of snapping. So essentially, what question A is asking is, find the acceleration when the tension is 393. Okay. Okay, so I drew my picture. Here's the box headed down. My velocity's down, acceleration's down. Okay, I drew the weight and the tension. So I did F equal ma. Mg points positive, because there's my coordinate system. Mg is positive. Tension points up. That's equal to ma. So here's A. Now, the only thing is, they don't give you the mass of the box, they give you the weight of the box. Okay, and again, you could find the mass, but I just multiply top and bottom by little g. That way I could use the weight of the box. Okay, so that gives me the acceleration. Okay, in part B, they want to know, okay, at that acceleration, what speed's going to hit the ground? Okay, so you start lowering it here. Okay, start lowering it here, and then it hits the ground over here. Okay, so two velocities, they give me a distance. That's equation number 3. So I used equation number 3 using that acceleration, and that gave me the speed with which it would hit the ground. Okay, so this problem is the opposite of the one above it. Okay, here's an elevator. This could be the box of roofing tiles. Okay, instead of lowering it, going faster, now you're raising it, going faster. Okay, so in this picture, okay, so for part A, I did over here, for part A, the elevator, okay, is moving upward, and they tell me it's accelerating upward. Speed is increasing. Okay, so I want to find the tension. So picture, forces, coordinate system, nothing to break up. So I'm going to do F equal ma in the y direction. So T points up, mg points down, that's equal to ma. This is the mass of the whole elevator. So I'm going to solve this for tension. Okay, and they give me the acceleration, so I put that right there. Okay, now again, they don't give me the mass of the elevator, they give me the weight, so I just multiplied by g over g. Okay, and then I can put in the weight as a number. Okay, and then I do have to divide by g. All right, so I never explicitly need to solve for the mass of the object. I think the last 2 problems were like that as well. That gives me the tension. Now, next one is it's still going upward, but the speed is decreasing. This is like an elevator coming up to the top floor and it's slowing down. So for part B, the speed is decreasing. Okay, so that says that the acceleration points downward. So in part B, okay, I drew the elevator, still headed up, but it's slowing down. Okay, the speed is decreasing. That's why the acceleration points downward. So the acceleration is negative 1.22. So same coordinate system, because you always want the acceleration to be positive. You want the acceleration to be negative when things are slowing down, and here acceleration is negative. Okay, so I did F equal ma in the y direction to that picture there. Okay, so tension points up, mg still points down, that's equal to ma. Solve it for t. This all looks the same, but number a is negative. Okay, so when that a goes in there, that's a negative number. Okay, so in 6, okay, so this thing is being constantly pushed. Okay, they give you the pushing force. Okay, they give you the mass of the book. They give you the distance. Okay, and they tell you if it starts from rest, it has a final speed. They want you to find the coefficient of kinetic friction. So they want you to find mu sub k. Okay, now the good news in these chapters is the only place mu sub k pops up is in that expression. Okay, so it's a force problem. Okay, so you're going to be using that somehow. So it's a Newton's second law 5-step method. So I have my picture, forces, I drew my forces. Okay, coordinate system, acceleration's to the right, my x is to the right. Nothing to break up, so I'm going to apply F equal ma in the x direction. So that's P points to the right, kinetic friction points to the left, that's equal to ma. But in this chapter, remember, static friction takes on values from 0 up until our contact is broken. Kinetic friction is a constant retarding force. Okay, so you can write kinetic friction as mu k times n. All right, so you can easily look at the picture and realize that n is equal to mg. So when I rewrote this, so if I call this equation 1, okay, and equation 2 and 3, I used 2 and 3 and substituted back into 1. So right here where I have kinetic friction, I put in mu sub k times n, and n is mg. Right? And then just solve that for mu sub k, and you have everything in here except for a, okay? But they give you a v initial, a v final, and a distance. So I can use equation number 3 to get the acceleration. So acceleration's a number, put it back there, and that gives you mu sub k. And you'll see that all the units do indeed cancel. Okay, this one's a little bit more involved. So they have a pig sliding down a ramp. But what you kind of have to assume is that the pig starts up here at the ramp and slides down. So it starts from rest. Okay, so what I did is I drew two pictures. It tells me that the pig will slide in twice the time it would take to slide down a frictionless ramp. So this picture here is no friction. So for example, if it takes 1 second to slide down the frictionless ramp, it's going to take longer to go down the rough ramp. Maybe it takes 2 seconds. So it says it takes twice the time. So I said, okay, here's my friction picture. The pig starts from rest, gets to the bottom in a time t2. This is picture 2. Picture number 1 has friction. The time it takes the pig to slide down, t1. T1 is twice that time. So if this took a second to go down, this one takes 2 seconds. It's twice the amount of time. Okay, so they tell me that T1 is 2 times T2. So essentially that means I need to find the time it takes the pig to slide down. So that's a kinematics problem. Okay, so equation number 3 doesn't have a T in it. Number 1 has a T in it, but I don't know V final, so that's why I'm using equation number 2. And I'm using the incline as my x-axis. Okay, so I used this form, delta x. Okay, so I'm using, this is going along the x-axis. I'm treating this as one dimension. Okay, so my delta x, V initial is 0, so 1/2 AT squared. Okay, so I'm trying to find time, because I have a relationship between these two times. So if I solve this for t, okay, solve that for t, okay, then I can go back and say, okay, T1 is equal to 2 T2. Right? So over here, this is T1. That's equal to 2 times T2. And that's what I have there. Okay. Now the delta x's are the same. It's the same distance it slides. So the delta x's cancel. The 2's cancel. You gotta be careful. And I'm left with this. Okay. All right, and then I squared both sides. I squared both sides of that, so square root went away, square root went away. This 2 became a 4, and I solve it for A2. So that says that for my two pictures, that was number 1, that was number 2, okay, that the frictionless acceleration is 4 times the acceleration of when it's rough, okay. Okay, so that says essentially I have to find acceleration for when it's frictionless, find the acceleration for where it's rough, and set A2 equal to 4A1. So now it becomes a Newton's second law problem. So I have all the force, I'll go back up here. I have all the forces drawn. So I did picture, forces, here's the pig. Okay, so I have the weight, normal force, kinetic friction, okay, picture forces, coordinate system. It's accelerating in that direction, so that dictates my coordinate system. I broke up mg, put 2 lines through that, all right? And then what I did is when I drew my picture over here when there's no friction, the only difference is there's no f sub k. So it's the exact same picture, but without the f sub k. All right? And then I just recopied this same picture down here. This is for when there's friction. Okay, so I'm trying to find A1. All right, so I did F equal MA in the x direction to the pig when there's friction. So mg sine points down, friction points up, and that's equal to M1A. Okay, remember friction is always mu sub k times the normal force. All right, so to find the normal force, I can just apply F equal MA, F equal MA in the y direction. So normal force points up, mg cosine points down. So normal force is mg cosine, all right? And then that's what I get to put right there. So this expression becomes mg sine minus kinetic friction, which is mu sub k n, okay? And the normal force is mg cosine. So I rewrote that right there. So here's mg sine minus kinetic friction, which is mu sub k, that's n. So the masses drop out, I can solve that for A. So this gives me A1. Okay, A2, this is picture 2. I just took the same picture, put it down here. It says the same picture as above, but there's no kinetic friction because it's frictionless. So to find A2, I supplied F equal ma in the x direction. The only thing that points downward is mg sine. That's equal to m2a, 2. Masses drop out, and that gives me what we remember from the kinematic dot lab. That's your dots. Right? The acceleration was g sine theta. That was your theoretical acceleration. So we go back to the expression above. A2 is 4a1. So here's a2, and that's equal to 4, and that's a1. Okay, and then just do a little bit of algebra, and then I get mu sub k is 3/4 tan theta. Okay, so I had to get a relationship between the times, and they gave me information to find that for time t1. Okay, so the time for the pig to go down the rough slide is twice the time it takes to go down the frictionless one. Okay, so whoops, this one was chapter 6. Okay, this one's also chapter 6. Okay, so the eyes have a person pushing a box. Okay, goes along the level floor. They give me mu sub k, and they want to know, for part A, they want to know what is F sub k, and then the crate's acceleration. So Newton's second law, I have a picture, I have my forces, coordinate systems based on the direction of A. Okay, for part A, they just want kinetic friction, and kinetic friction is always equal mu k times the normal force. And you go look at that picture and tell that the normal force is mg. So then kinetic friction is just mu sub k times the normal force, and then you get a number. That's part A, done. B, they want the acceleration. So now you're doing step 5. Okay, you do F equal ma in the x direction. So P points to the right, Fk points to the left, that's why it's negative. That's equal to ma, and then you already have F sub k as a number from the previous problem, and that gets you A. Okay, so question 7 is good because it's a good exercise on being careful with finding the normal force. That's chapter 6. Okay, so if I look at this, I have a crate being dragged across the floor. Person's pulling on it, let's say with a rope. Okay, and first they want to know, if given the coefficient of static friction is 0.5, what's the minimum force required just to break contact and have it move? Okay, so I have my pulling force P, I have normal force mg. Okay, now if I'm not pulling, if P is 0, there's no static friction. Okay, but as soon as I start to pull, that static friction force points to the left. And if I want to find the minimum pulling force to break contact, we have to remember that contact's broken when the static friction force is at its maximum value. And the maximum value is mu n. Okay, so what is n? Now be careful, you can't say n is mg. Okay, that's because you have this other force up here because you're trying to kind of lift it. You're lifting the box upward, which would reduce the normal force. So if you had a scale under the box and you're pulling upward on the rope, that's at scale would actually be less because you're trying to lift it off of the floor. Okay, so you have to find n. Okay, so again, it's not moving. So I have my picture. Okay, so to find n, that's in the y direction. So I'm going to do F equal ma in the y direction. Let's see. Whoops. I'm trying to find, let's see. So I want to find n. No, I'm sorry. I need to find p. I need to find the force p. Okay, so that's why I'm doing F equal ma in the x direction. So that should be F equal ma in the x direction. That's an x. Okay, so I look at my picture. So P cosine points to the right, static friction points back, and that's equal to 0. It's not accelerating. You're trying to break contact. Okay, so that gives me P cosine is static friction. I'm trying to find P, okay, the pulling force P. All right. Remember, static friction, you're trying to find P to break contact. So static friction is equal to its biggest value. It's equal to mu n. Okay, so P cosine theta is mu n, but I don't know what n is. So that's where you have to be careful. That's when you can't say n is mg. Okay, so now I do F equal ma in the y direction. Look at my picture. So P sign points up, N points up, mg points down. So if I solve it for N, okay, N is equal to mg minus a little bit, like I said, because you're pulling upward and that thing is trying to lift off the floor. Okay, so I call this equation 1. I call this equation 2. So I'm going to take this N and stick it right there. Okay, so I have P cosine theta. P cosine theta is mu N, and that whole thing is N. Right? And then just have to be really careful. I would take the mu sub S, P sign, bring it over to the left, factor out letter P, divide by this stuff. Okay, so just be careful of the algebra. So that gives me the pulling force. Okay, so this thing, that's 256. So if I start to pull on this thing, contact isn't broken until P reaches 256. Okay, now they say if mu sub k, so contact now breaks. Okay, if mu sub k is 0.39, what acceleration does this thing now get? So I have the same picture. Now contact's broken, so this is now kinetic friction. So now it is accelerating to the right. Okay, so I want to find the acceleration. So that's a Newton's law problem. I got picture, forces, coordinate system. I broke up force P. So I'm going to apply F equal ma in the x direction. So P cosine minus F sub k. Okay, again, I'm trying to find A. Okay, so in these chapters, kinetic friction is constant. It's always equal to mu sub kn. Right? And from above, we had this. Normal force is mg minus p sine. Normal force is mg minus p sine. So that gets to go right there. So p cosine minus f sub k. F sub k is mu sub k times n. That's equal to ma. And then just do the algebra to solve for A. That gives you the acceleration. Okay, so this is also chapter 6. Okay, so here you have someone hanging from a beam. So I drew it looking at it from here. So here's a side view. Okay, so in black I have one hand and in blue I have the other hand holding on to the same beam. So let's say this is your thumb. So N2 would be your thumb pressing against the beam. N1 would be your fingers pressing, okay, for the same hand. And N3 and 4 would be the other thumb and the other fingers pressing inward, okay. So these are the normal forces that the person exerts on the beam, all right. But since nothing's accelerating, acceleration 0, okay, nothing's moving, then N1 would cancel out N2. Okay. Or if I applied F equal ma, okay, let's say to the beam in the x direction, that says N1 would be equal to N2. So these two forces are the same. Same for the other hand. Nothing's moving left and right. So instead of there being an N1, an N2, an N3, and N4, all those N's are the same. There's no acceleration in the x direction. So we're going to simplify this. I know there's 4 fingers on one side, but we're going to say there's 4 points of contact where you have a force. So you have one from that side, there, and there. Okay, so there's 4 normal forces horizontally on the beam. Okay, that's forces on the beam. Okay, so when I draw the picture here, so here's the same beam. Okay, here's the person there. All right, so instead of drawing their hand up here, I just drew the 4 points, the 4 contact points. That's these black dots here. Okay, so this would be, let's say, a thumb. That'd be your 4 fingers from the same hand. So let's say this thumb presses inward on the beam, and the beam presses backward on your thumb. So these blue normal forces are the forces on him, but they're all horizontally, and he's not accelerating horizontally, so all these normal forces cancel. Okay, so I'm drawing the forces that act on the person. So you have the weight. Okay, now he's holding onto the beam with 4 points of contact through his hands. So if he releases his grip, he would start to slip down. Okay, friction prevents him from slipping down. So everywhere there's a contact point. So on this hand, you have a thumb and a forefinger contact point. So let's see, this would be static friction for the thumb. This would be static friction for the fingers. So the hand wants to slide down. Friction prevents those from sliding down. They point up. The other hand, you'd have, let's say, a thumb and the forefinger contact point. Person wants to slide down. Friction prevents that from happening. So all these 4 blue forces are the 4 friction forces due to these 4 points of contact. Each hand has 2 points of contact. Okay, so he's pressing hard. And I said as he releases his pressing force, okay, as his normal force gets smaller, he's going to slip. So that's why those friction forces point up. And they're asking, okay, what's the least magnitude of the normal force? So if he's pressing really hard and he's hanging there, and he starts to release his grip, okay, what's the smallest force he can hold the grip before he starts to slip? Okay, so I drew the forces that act on him. I'm applying F equal ma in the y direction. He's not moving. Okay, so I have 4 friction forces that point up, and I have mg that points down. So those 4 point up, that points down, and that's equal to 0. So I wrote this over here, and then remember static friction, because he's releasing his grip and he's about to slip. So static friction is equal to its biggest value. That's where it's equal to mu n. So where I have static friction, I can put in mu n, and I can solve that for n. Okay, so that's what they have as the answer, but convert that to pounds. It's about 60 pounds. So if you took a scale and gripped it between your thumb and fingers, that means you would have to press so that the scale would read 61 pounds. Okay, so that's an enormous amount of force to press to be able to support yourself on a beam like that. Okay, so this picture here, okay, you have a rock, big chunk of rock, okay, and in part A, so I just made it bigger over here, in part A, okay, that force that's drawn up there, that purple force F, okay, that's not in the problem until part B. So here what they're saying that for part A, that there's a separation here. There's nothing in between here, okay? And they want to know, will the block slide? Okay, so they gave me the mass of the block, okay? And they want to know there's friction between this rock, okay, and the bed. And they want to know, is this thing going to slide? So what I did is I drew the forces that acted on that big chunk, that big rock. So you have the weight, okay, you have the normal force, and you have the friction force. So this whole big chunk, that big green chunk, wants to slide down. Friction prevents that from sliding down. Okay, so they want to know, is it going to slide? Well, this whole thing, this whole block would break contact with that tilted bed. Okay, would break contact with that line. Okay, well, I should say, if it breaks contact, that means static friction is at its biggest value. And the largest static friction can get is mu n. Okay, so what I did is I calculated over here, okay, what is the biggest static friction could be? Well, it's mu n. Okay, so I had to find out what is n. Well, that's a Newton's second law problem. So I drew the picture, forces, coordinate system. Okay, it's not moving. So I broke up mg cosine. So I did F equal ma to this large block in the y direction. So n points that direction, mg cosine points down. So normal force is mg cosine. So static friction is mu sub s times n, and so that's what I put in for n. So this gives me a number for the biggest the friction force can be. Okay, so here's that big chunk of rock. I have mg sine points down and friction points up. Well, how big is mg sine? Okay, well, I just calculated mg sine. I put in numbers and I got that. So that number is small and that number is big. So that says that mg sine is less than the maximum static friction. So mg sine isn't big enough to have or to break contact between the rock and that inclined bed. So they ask, will it break? No. Second part of the problem is now this purple force here, okay, is due to, you have ice, expansion of ice, and it's pushing downward. That's now that green arrow. Okay, and they want to find what's the minimum force required to break contact. Okay, well again, contact is broken when static friction is mu n. So I have the same diagram I had before, except now I have that additional force. Okay, I have that additional purple force F. So I applied F equal ma in the x direction. I want to know when contact's broken, so acceleration is 0. So I have that purple force F points down, mg sine points down, static friction max points up. Okay, and then just solve that for that purple expansion force. Okay, and remember from the previous problem, static friction was that number from above, and so I find that expansion joint force comes out to be that. So it's a difference between that number and mg sine. Okay, so another problem from chapter 6 is you have something going around in a circle. So this is a top view. So you have a cat here, this thing's going around in a circle, all right, and eventually if this thing goes too fast or if this surface is too smooth, the cat will slip. So I drew a front view. Here's the center of curvature, that's the cat, okay, accelerating toward the center. So they want to know what's the smoothest this surface can be for the cat at that radius, at that speed. They give me a speed. Okay, what's the smallest the coefficient of static friction can be before this thing begins to slip? So that's a Newton's second law problem. So I have my picture, forces, coordinate systems based on the acceleration, okay, which is toward the center. So I didn't have to break up anything. Okay, so my static friction is my centripetal force. Okay, so I'm going to apply F equal ma, right? So eventually when I do that, I'll have a v squared. But they give me v, but they don't give it to me in the correct units. They say that the rotation rate is 1 revolution in 6.2 seconds. So that's v. Okay, it's a rotational speed. So we want to convert it so that it's a speed in distance per time. So I took 1 revolution every 6.2 seconds, and I said that in 1 revolution I have 2 pi r. I have 2 pi r meters. So now that's my speed in the correct units, in meters per second. Okay, so to find the smallest coefficient of static friction, okay, at which the cat would slip, that means it's on the verge of slipping, so static friction would be equal to its biggest value for that speed. It's equal to mu n. So when I apply F equal ma for step 5, okay, I do net force centripetal equals ma centripetal. Okay, static friction is my centripetal force. That's equal to mv squared over r. But static friction is mu n, okay, and normal force is mg. So right here, I put in mu n, where n is mg. So static friction is mu times the normal force. And then just solve that for mu. And then just be careful because I'm squaring that whole thing, which is v. Okay? And it should be uniless, and sure enough it is if you check the units. Okay, so here they give me 2 pieces of information. They tell me that when they pass over the top, okay, the normal force is 0. So that person would feel weightless here. So speed is constant, so they're saying if they're weightless up at the top, okay, it asks what's the normal force on the driver from the seat. So essentially, remember, normal force is what you feel. So if you're going at constant speed on this road, if you feel weightless up here, they're asking what do you feel when you're at the bottom of a dip. Okay, so essentially they're asking to find the normal force. So that's a Newton's second law problem. So we have picture, forces, okay, normal force, that's the force that the seat exerts on the person, that's upward, they have their weight. There's my center of curvature. Picture forces, coordinate system. Here I'm not even going to draw x and y. My centripetal is toward the center, nothing to break up. Okay, so when I apply F equal ma in the centripetal direction, I look at my picture, n points up, mg points down, okay, and that's equal to mv squared over r. So I can solve that for n. Now I need to find v. Well, to find V, I'm going to use the information from the top picture. Okay? They tell me when they're up at the top that they feel weightless. So I go to that top picture. Normal force is 0. All I have is the weight mg that points down. So that allows me to find the speed v. So if I apply F equal ma, so I did the 5-step method up here. I have picture, forces, coordinate systems based on the direction of acceleration, nothing to break up. Here's step 5. So F equal ma centripetal. So mg points down, mv squared over r, masses cancel. Okay, that means everything in the car would be weightless. Okay, and then this gives me v, solve that for v, and then I can put that back right there. Okay, so actually v squared is gr. So up at the top here where I had a v squared, I put gr. So the r's cancel, I have mg plus mg. So in this picture, if they feel weightless at the top, going at a constant speed, they would feel twice their weight at the bottom. And that's because both of these things have the same radius. Okay, so weightless at the top, and then twice their weight at the bottom. Okay, so here's one, this is also chapter 6, right, where this thing is going around in a circle, okay, on a frictionless table, and it keeps, and this one doesn't fall to the ground because there's a tension. There's a string tension that prevents it. And the tension is due to this thing going around in a circle. And that's what they want you to find. They want you to find what speed for this little puck going around prevents this thing from falling down. Okay, so I drew the picture. This thing's going around in a circle. Okay, here's the string that goes through the hole. All right, so I'm trying to find that speed. So V is wrapped up into that term. So that's why it's a Newton's second law problem. So I drew the forces on the puck. Okay, I didn't need to draw a normal force in mg here, okay, because I'm doing this in the centripetal direction, okay, and that's in a plane that's perpendicular to mg and n. Okay, so picture forces, my coordinate system is toward the center, nothing to break up. So there's the tension force, there's T, and that's equal to mv squared over r. Okay, but what is T? Well, this one down here, that thing's not moving. Okay, so the tension is the same everywhere in the string. So that tension is just the weight of that big block. Okay, so tension is capital mg. So I put that there. Okay, careful, masses don't cancel. It's two different masses, and that gives you the speed. And that'll be some number in meters per second. Okay. Okay, now this one is a little bit more, not involved, but you have to be really careful. So here's a bike coming at you. All right. They give you the radius of curvature. They give you a constant speed. They give you the mass of everything here. And first they want to find the friction force on the bike from the road. So I drew a front view. Okay, so this thing is my bicycle. Okay, it looks like the front tire. Okay, so I drew the forces on the bike. I have the weight, I have the normal force, and I have the static friction between the tires and the road. So there's my radius of curvature. Okay, there's the center of curvature. I'm accelerating toward the center. Okay, and they want to find the force of friction on the bike from the road. So part A is they want static friction. So that's a Newton's law problem. So I applied net force centripetal as ma centripetal. So static friction points to the left. Okay, and that's equal to mv squared over r. Okay, so they give me m, they give me v, and they give me that. Done. So I have static friction. Okay, now they want, for part B, they're not asking for the net force, because net force is ma. Okay, they're asking for the net force on the bike from the road. Okay, so you got to remember there's three forces. This force is exerted by the road. This force is exerted by the road. This force is exerted by the earth. So the net force would be the sum of all three. Okay, they're asking I should say the net force on the bike due to all forces would be the sum of all three. They just want the force exerted on the bike from the road. So they want the net force exerted on the bike by the road. That's only static friction and the normal force. So they want the vector sum of those two. Okay, remember, mg is a force on the bike that's exerted by the earth. So I took this picture up here, redrew it here, and so essentially it's, you just make a box. It's Pythagorean theorem. So if I want this force here, okay, I just do Pythagorean theorem. That thing squared plus that thing squared, square root. So this arrow here, okay, that's 877, all right? Okay, so that's what they want you to find in part B. This is the net force exerted on the bike by the road, all right? So remember, the net force on the bike due to all forces is ma. So remember, there's three forces. That's due to the road, that's due to the road, that's due to the earth. So if I added them head to tail method, that vector plus that vector plus that vector, here's n plus static friction plus mg, and the net force, okay, here's where I start, here's where I wind up. Net force is this big red vector which points to the left, okay, and indeed, that's my net centripetal force, right? It's to the left. So part B did not ask you for that. They just wanted the net force exerted on the bike due to the road, and that was those two.